All right, let's run through this. Overall, this was really good. Some people got kind of nickeled and dimed with like little things here and there, 1, 2, 3 points, and it kind of adds up, and that can bring your score down. This is us. But by and large, mostly it looked like people were pretty confident in what they were doing. So if I don't go over something and you have questions, just go ahead and ask while we're talking about it, because some of this I'll go through more quickly than others. So structure name data, which will be used to hold the following items. So if you want to hold a string, the really kind of best way to do that is character star. So what was our string called here? Level. Bless you.
Thank you.
So char star level. Sometimes you can use bracket brackets, sometimes you can't. Inside here, if you don't know the length, that's one of those cases where you can't use the bracket bracket. It'll tell you that's illegal when you try to compile. But you can't really go wrong with char star. Right, you're saying this is a pointer to a character. That's what a string is, okay? String is not a predefined type in standard C. You got to make it a char star. So single character is just a char, integer is just an int, and an array of integers named numbers is int variable name. And then you can say bracket size of the array. So write a statement to define a structure named data containing the above fields. So that's just your struct statement, right? And I think everybody had the basic setup for that. Struct data. Curly bracket. All of these fields, close curly bracket, semicolon. And then write a statement declaring a variable named code to have type struct data star. So this is a declaration. So type a variable, which in this case is a struct data star because you want a pointer to it, and you're making a variable called code. So that's your whole declaration. If you say equals malloc, you're doing more than just declaring it, you're actually initializing it. Okay, so all variables have two steps to their creation. You have to declare it and you have to initialize it. Well, you don't always have to initialize it, but it does no good if you don't. So this is a declaration. And then the third part was to use a malloc statement to set the code variable to point to a block of memory large enough to contain. So, and you could do that in the same statement, except that I broke it up into two questions. So code equals malloc. Malloc takes an integer, it's the number of bytes. Okay, we don't know how many bytes we need for all of this stuff, and even if we add up the size of each of these, we've seen that doesn't guarantee you've got enough space for the structure. So the way to find out how much space you need is to say size of, and then put in a type of variable. Okay, the type of variable we want is a struct data, not a struct data star. So size of parentheses struct data will tell you how much stuff you need to store all of that, how many bytes. All right, and then the initialization code. So you want to set level equal to x17. That's a string. It's a char star. Strings have to go in double quotes. If you use a single quote, it will assign it some small integer, and when you try to use it, you'll segfault. XC is a character that can hold a single byte. That's a single quote W. Okay, so that's a string, which is actually the address of somewhere in memory where an X and a 1 and a 7 are stored. And this is just a single character, which is just 1 byte. And you're safe saying something like code arrow level equals this thing. Because the compiler, when it sees double quote x17, it does two things. One, it finds a section in memory that's big enough to hold 4 bytes, and it arranges to have those 4 bytes filled with an x, a 1, a 7, and a null terminator. And then it replaces this with the address in memory where it's storing that first character. So when you do this, code arrow level equals, you're really taking that char star and you're setting it equal to the address of that x. So now level is a string that basically contains x17 in a null terminator. You could try to do something like this, like string copy, code level x17. And string copy is going to go byte by byte and read a byte here and store it in successive locations here. But if you do that, you've got to initialize what char star level is first. Otherwise, it's probably null. And when you start to do this, you get a seg fault. So this is one of the cases where you're actually better off just saying equals some double quoted string. All right, and lots of people use dot instead of arrow. Just remember to use an arrow if you have a pointer, a dot if you don't have a pointer. What's your last name?
Chris.
Yeah.
Thank you.
All right, linked list question. So, got a linked list, it's got a sentinel, it's got 3 nodes. I'll just do this off of here. All right, we've got a linked list. This is linked list arrow next. All right, because that's LL. So LL next is this block. LL next next is that block. LL next 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 is that block. I never try to make any sort of pattern out of this stuff when I do these kinds of problems, because the patterns aren't always the same. I just go through this sort of detailed exercise each time. So it will be printed by LL next next data and LL next data. Well, this is LL next next, so LL next next data is 24. And then LL next data, this is LL next, so its data is minus 99. So this should print 24 followed by minus 99. And most people got that right. All right, write some C code to delete the last node of the list without using any loops or conditional statements. So the fancy way to do it is to free LL next 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 and then set LL next 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 equal to null. But that's, obviously prone to error if you have too many or too few of those nexts. So a few people did this, and I thought this was great. So let's put our list right there. So first equals LL next. Second equals first next. Last equals second next. So what are we doing? Unambiguously, we're saying this node is pointed to by first, this is pointed to by second, this is pointed to by last. And now I got 4 variables, LL, first, second, and last. Each one points to one of my nodes. I can do anything I want now, right? You're totally unstoppable at this point. So what do you want to do? You want to delete this last node from the list. So I want to set second next equal to null. Right? Pop a null right in there. This is no longer part of the list. And then I want to free this last node from memory. Just free last. So it's 5 lines instead of 2, but it's so less likely to have a small error like having too many or too few arrow nexts. If you do the one size fits all, right, this is LL. This is LL next, this is LL next next, this is LL next next next. So I want to free this node from memory, and then I want to set this block, which is LL next next next, equal to null. And in this case, you've got to free before you do this, because if I said LL next 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 equal to null first, this becomes a null. Now when I try to free LL next next next, I'm trying to free null. So in this case, you've got to free this node before you change this. But in other things that we've done, we've said very explicitly, make sure you use this node before you free it. Right? So there's not really a one-size-fits-all magic rule you can just always apply, always free before you use, or vice versa, right? You really gotta work through the problem itself. All right, so that'll delete that last node, and then write some C code to insert a node with value 0, or to create a node with value 0. So create a new node with a data value of 0, so you're going to have to call malloc. Again, size of struct node. And we got to call this something. Well, eventually we're going to point to this with a variable named new, so we may as well just call it that right now. Struct node star new equals that. And then you want it to have a data value of 0, so new arrow data equals 0. So now I've got another block up here, which I'll call new. It has a 0, and we didn't do anything with that next field. So now insert that new node between the -99 and the 24. Again, if you've got these names, if you're calling this first and you're calling this second, this is pretty straightforward. New next equals second. First next equals new. Right, because what do I want to do? I want to have this point over there, and I want to have first point to my new node. If you try to do it without any temporary variables, this first statement is new next. Okay, that's this field right here. Is equal to LL next next. That's this node. And then LL next next is equal to new. And you have to do it in that order, because if I do LL next next equals new, and then I set new next equal to LL next next, I'm setting new next equal to new. Right, so I want to use this value before I change it. All right, the other thing, if you're doing something like this, don't say first equals malloc size of struct node and then say first equals LL next. That's a memory leak. Right? Only malloc when you actually want to create one of these new blocks. If I'm just making something that's going to point somewhere, all you have to do is declare it struct node star first. And then I can say first equals LL next or whatever. All right, and this one was very good. So writing a function that counts the number of nodes containing a data field equal to x. Again, the only recurring issues I saw were startup and shutdown, right? The edge cases. So our usual struct node, we want a function named count. Takes a pointer, returns an int. So the way I like to think about this, I want something that's always pointing to the node I'm currently thinking about. And I don't want to look at the data value in the sentinel, so I'm going to start off by skipping that. So set sentinel to whatever the sentinel's pointing to. And this is always safe because the sentinel exists. Sent is never null. Right? That's why we have a sentinel. So this will be the first node unless the list is empty, in which case now sent is going to be null. So I can just while sent is not null. If it's not null, see if it's equal to x. And if it is, increment some count. So initialize, I'll just call it C. So initialize some count to 0. And then just return your count. But there's other things you can do. You can skip this and you can say, well, sent next is not null, and then see if sent next is equal to x. And we've played with this before in class, right?
Is there an increment that I'm not seeing in there?
Plus plus c?
Yeah, for the count, but what about to go to the next node?
Oh, thank you. Yeah, I got an infinite loop. Cool. How much would that have cost me on my test? 3 points, yeah. All right, good catch. Yeah, so do that inside the while loop. All right. So typical issues: counting the sentinel's data value, not counting the last node's data value, going one spot too far. Like, well, sentinel is not null, set sentinel equal to sentinel next, and then use sentinel data, and you're going to seg fault at the end. Doing mallocs that you didn't need to do. Not initializing your counter, forgetting to increment your counter, forgetting to check to see if the data value is equal to x. Printing, don't print, right? Functions usually don't print. It's very rare to call a function and have that function print something. Printf is one of those exceptions. Printf is supposed to produce output to the screen. Most functions don't print, right? If you're writing a function and it's got a print statement in it, be really, really sure that that's within the spec of the function. Almost never do we print from inside a function. Usually functions return things and leave it up to the caller to print. If the caller wants to print, it's easy to do. But if you don't want to generate output and your function generates output, you can't use that function. So in this case, there's no printing being done anywhere. So watch out for that. A few people did this recursively, which is okay. I like recursion. It can be tricky to do that, especially with sentinel nodes. And it can be expensive memory-wise. Okay, recursion on a list takes memory on order of n, where n is the size of the list, the number of nodes. So that can get you into memory problems, but I was happy to see recursion, so you got full credit for that if the routine worked. All right, queues. So I don't know what I did this quarter, but I did something really bad when I talked about queues, because there's a lot of confusion about queues. Probably not as much about stacks, but people are really kind of have an overly complicated view of what queues are about, and that's got to be my bad. So let me say this about queues. So as an abstract data type, a queue is just a collection of data, stuff. Okay? You can add things to the queue, you can remove things from the queue. That's basically it. Okay? But it has the property that you add things one at a time, and when you remove things, they get removed in the same order that they were added. That's the essential property of a queue. It's just a place where you can add a bunch of stuff one at a time, and then at some point you can start removing things and they get removed in the same order. Forget about head and tail and head equals tail and circular buffers and all that kind of stuff. Okay, for now just think a bunch of stuff you throw in there and you pull them out in the same order they were put in. Okay, and the physical model to keep in mind is a line of people. Right, there's the front of the line and there's the back of the line. And whoever gets to the line first, they're at the front of the line, they're the first one who goes out of the line. Okay, so because we're computer scientists, we need fancy terms. So we call the front of the line the head, and we call the back of the line the tail. All right, so head and tail are just, they're telling you where the head of the line is, where the back of the line is. Okay? If the line's empty, head and tail are kind of meaningless. If there's one thing in the queue, right, the head and the tail are kind of, referring to the same location, right? But when we implement this with arrays, we did specific things with the variables called head and tail, right? And we set them both equal to 0, and then we used an if statement to see if the queue was empty by seeing if head and tail are equal. And when we insert, we increment one of them and we roll over and all this kind of stuff. But abstractly, just kind of think of the head is, the part of the queue where the thing that's going to come out first is sitting. And the tail is the other end of the queue, right? So even though it's just a collection of stuff, it's convenient to think of them as being stored in a big long line, right, or a queue. And so the tail is the back end, the head is the front end. That's really all that's going on here. And when we implement with a linked list, or we implement with an array, or a pair of arrays, or whatever we decide to do, right? These things have very specific meanings, but abstractly, that's straightforward. So, and I should have said, as an abstract queue or something, but here's all I was looking for, okay? And most people got this, but they also did a lot of extra work. Insert a 20 into the queue. Okay, your queue has one thing, which is a 20. Insert two things, you've got a 20 and a 12. The 20 is at the head, the 12 is at the tail. Do a remove, the 20 goes out, now you've got a 12. Insert a 25, you've got a 12 and a 25. The 25 is at the tail now. 12 is at the head. Do a remove, the 12 comes out, your queue just has a 25. Insert a 30, you got a 25 at the head and a 30 at the tail. And remove, you've got a 30 again. Right, so I was trying to do something which didn't have programming involved, but I think it made it way more complex. So if you insert a 35, your queue is going to look like this. If you insert a 15 now, your queue is going to look like that. And again, if you draw an array, it's going to look different. And if you draw a linked list, it's going to look different. But as kind of an abstract data type, it's just a bunch of numbers set up so that we remove them in the same order we insert them. And the way we typically visualize that is by putting them in some kind of linear arrangement, where we're going in on one side and coming out the other. So if I ask you about queues on the final, I'll make sure there's programming involved, because I actually think that would have been easier for you. All right, so short answer questions. Which of the following is not part of an abstract definition of a stack? What's a stack? It's a collection of data. You can push things to the stack, you can pop things, and it removes things, it pops things in the reverse order of how you push them. And you can see if it's full and you can see if it's empty. So, so push X, definitely. Y equals pop, definitely. If is full, return, definitely. If SP equals 0, return, that's an implementation level view of a stack, right? If you implement your stack with an array, there's an SP variable. If you implement it with a list, there's no SP variable, right? And if you implement with an array, maybe I set my stack pointer equal to 100 when the stack's empty. And maybe it only grows to 1, maybe it can never get to 0, right? So you're assuming things about the implementation of your stack on part C there. So C is not part of the abstract definition. Potential seg faults. So integer x, y equals ampersand x. All right, so integer x, that's going to declare x to be an integer. It has some value, but we don't know what that value is. It's probably like 519,000 something, right? Y equals ampersand x, that sets y equal to the address of x, where x is stored in memory. That's well defined. We don't know where x is stored, but this will tell us where it's stored, and this sets y equal to it. And now if we print out y, we're just printing a memory address. So that's completely safe. This third one, integer x, y, z equals x plus y, print z. Nothing can go wrong there. Okay, we don't know the values of x and y, so z is going to look like some weird number, but it's just going to print a weird number. And part D, integer x, integer star y, y equals the address of x, and then print star y. This asks to print the thing that y points to. Well, y is the address of x. The thing it points to is x. So this is just a fancy way of printing the value of x. We don't know what it is, but again, you can't segfault from that. Question B, probably guaranteed to segfault. Because we declare x to be a pointer to an inch, we don't give it a value, so we don't know what x is pointing at. But whatever it's pointing at, we try to set y equal to that. That's probably going to segfault. So B is the answer there. Allocate enough space for an array of 125 elements of type big. So malloc size of struct big. This is however many bytes you need for one struct big. If you multiply by 125, you get 125 times that space. That's enough space for 125 elements of type struct big. And if you do something, so I think that's all I was looking for was a malloc statement, but if you do something like struct big x equals, right, it will actually let you treat x as an array. And when you put in an index, it'll scale it up by the size of struct big because it knows that's what kind of array it is. Now you can also get away with this. Right, and technically that allocates enough storage for 125 elements, but that's a compile time or a link time allocation, not a runtime. I didn't ask for runtime. I will next time. This happens basically when your program starts executing, or that chunk of code gets loaded in. This happens when this statement gets executed. Same effect in the end, different locations in memory. What utility helps you detect memory leaks? Valgrind. All right. Compile a program named main.c if you intend to use GDB to debug it. All you need is gcc-g main.c. If you want, you can also say -o, you know, my executable, and if I want to call my program my executable, and so on and so forth. You don't want to use -c because that says don't make an executable. That says just build an object. That would create a main.o, and then you'd have to say gcc-g main.o. But this would be sufficient. This would be preferred. If your directory contains a make file designed to build a single program, what command do you type to build the program using the make file? You just say make. If you know what the name of the target is in the make file, you can say make specific target name, right? But you can also just say make and it'll build the first target that's listed in the make file. So if you said make program, I put a line through that, but I didn't take off points for it. But usually you would just say make. Allocate 10 bytes of data and assign a variable named pointer to point to it. Pointer equals malloc 10. That's all you need. So malloc takes an integer and returns that many bytes of storage. True statements about hashes. So hashes improve the efficiency of storing a key data pair versus using parallel arrays. That is definitely true, at least that's the intent. Hashes take less space than a pair of parallel arrays. No, they both have parallel arrays basically, or an array of structures, but it's going to be on par, the same amount of space. Hashes improve the efficiency of deleting a key data pair. That's also true. Hashes can only handle keys that are null terminated. That's not true at all. You could have your key be anything. When we looked at a DBM example, I threw null terminators in there so it would simplify printing, but doesn't care what your keys are. Right? Null termination of a string is a C concept, and it's just a convenience, so we don't have to pass around the length of the string. But when we get to Java, we're never going to say null terminated string again. That's not true, but we won't say it often. Most appropriate data structure for handling customers in a checkout line. That would pretty obviously be a queue. I think everybody got that. That's the example we've been using, because in the checkout line, you kind of want the first person in line to be the first person you help. It's really annoying when you're standing in line, you've been in line for 10 minutes, you're at the back of the line, and you're working your way up to the front, and 10 people come behind you, and they open up a new register, and they grab the person at the back of the line, and suddenly they get to go next. Right? That's throwing in like a queue-based processing, which is annoying. So yeah, usually a queue. Primary purpose of a hash function is to take a key and figure out where to store it, by finding an index. Right, so it maps keys to numeric indices. All right, so any questions on midterm topics? All right, so let's hop over to the server. Let's learn how to spell. I may not have a connection. I'm getting killed, man. I'm down to 5th place. I'm dropping fast.
Can't get past 3rd place.
I know, you're doing great, man. All right. And I think I mentioned it, but the HJKL you use in there, that's how you get around in VI if you don't have arrow keys or you don't want to use them. And so this is like good VI practice, right? Because you don't have to move all the way down to the arrow keys, and it makes a difference. All right, so we got 3 ODPs queued up, 211, 212, and 215. Finally, order is restored. So 211 is open right now, okay, and it's due tomorrow morning at 8. And then Tuesday morning 212 will open, and then Wednesday morning 215 will open. And those are on Canvas, right? And they become available once the assignment's open, so you can double check there to see which one is live. So 211, you're building a small tree manually. Okay, so you're going to be working throughout with this structure T node. It's a tree node. It has a piece of data which is an integer, and then left and right pointers called left and right that also point to tree nodes. And you're implementing a function called small. Okay, it takes 3 integers and it returns a pointer to a struct T node. What it's going to return is the root of a small tree that you're building, whose root node contains the value root, left node contains left, right node contains right, everything else is a null pointer. So if you say small, I don't know, 10, negative 20, and 50, that should build a node, a tree that looks like this. And it should return the address of that root. So take 3 integers, build a tree, there's the details of it, return the address of the root. The test bed is not that. Test bed is that. All right. So the test bed is main 211.0, no dash. So how do you do this? Well, you're going to do malloc 3 times to create your 3 nodes. So malloc struct T node, call it root, malloc another struct T node, call it L, malloc another struct T node, call it R, and then write a bunch of assignment statements to set this thing up the way you want. So whatever your root is, set the data equal to this, set left equal to whatever that left node is that you created, set this node arrow right equal to whatever the right node is you created. Go in here, set the data to -20, set the arrow left and right to null, set the data to whatever that third argument is, 50, whatever, set arrow left, right to null, and then return the address of that root. You should be good.
So no linked list there.
There's no linked list in here. Strictly a tree. There's no sentinel node. All right, does that make sense what you're after?
We don't need sentinel nodes.
No sentinel nodes with trees. Right, so your address of this root, that's actually the address of this node, which is the root of the tree. And once you have done this, right, you can use this when you're writing tree code if you want to build a traversal function. Right, you can cobble together a tree like this and then pass it to your traverse function and see if it prints it out in the right order, or whatever function you want to debug and develop. So it's useful to be able to build trees manually. And it doesn't have to be a simple tree, right? You could malloc 7 nodes and you know, build something up like that if you want. Or build something with 6 nodes and then call your insert function and call your traverse function. So as we go through and we work towards PA4, which I'll probably go over before Friday, you really want to be in the mindset of sort of testing as you develop, right? Because these functions are going to be more complex, there's going to be more of them, and if you're not quite sure how to do this or that, and you write 300 lines of code, and it turns out there was something you didn't understand, then you're going to have to rewrite 300 lines of code. So do this ODP, you can build a simple tree, work on a traverse function next. All right, we'll go through functions in PA4, but work on something that takes a tree and prints the values of all the nodes in a particular order. And you can test it by feeding it your tree. And once you have the ability to print the contents of a tree in a certain order, now you can do more complex functions and you can see how your trees are being modified because you have something that'll print the contents of the tree. So you can say, okay, let's make something that adds a node to a tree, and then call your print function, see if the nodes come out in the right order. And so you're going to want to build using what you've already developed to help you develop the next levels up. And then by the end you get to your delete function and you've got all this other stuff that you know works and you're comfortable with, and now you're only working on that little piece of your assignment, which is to delete the root of a tree. All right, so that's 212. Sorry, that's 211. And then 212 is going to add a node to a tree. And so this opens up tomorrow at 8, but if you want to work on it before class. Basically, it's going to take the address of a root node, and it's just going to be a root. It's not going to have any children. And you're going to take an integer n, you're going to build a new node and tack that to either the left or the right of the root. So there's no moving down, the root just stands by itself right now. And you're going to add one node to the left or the right, depending on whether your number is less than or greater than the root's value. And so you're going to end up with a tree with 2 nodes, the original root and the node you just added. That make sense? All right, PA3, let me give you a couple of reminders. Number 1, make sure you run valgrind on PA3. Okay, you don't want any memory leaks. If you figured out how to free all your memory in PA2, your code will probably work the same. Just call it on your stack list and call it on your queue list. if you didn't succeed in freeing all your memory in PA2, right, come and talk to me, and let's look at what you were doing. And it's usually an edge case. Either you forgot the sentinel, or you tried to free one node too many or something. But get that nailed down, it'll work for both. The other thing for PA3, please don't generate any excess output, okay? Because I have to go through a lot of test cases, and it's really a slowdown if I have to scroll through 10 lines of output every time I type in a command. So make sure you're doing what PA3 sample does under /temp, right? When you say stacker queue, print out the contents of the stacker queue on one line, separated by spaces with the head and tail or the top of the stack is indicated, right? When you say P for print the value that you're removing from the structure, and that's all, right? When you insert, go ahead and insert, and try to just do what the assignment's asking for. Okay, and like I say, if you're in doubt, go back to the PA3 sample that I posted on the server. If you're generating more output than that, if you're clearing the screen every time a command's entered or printing out usage instructions every time or something like that, right, you'll see it's quite a difference. So try to stick to just what's being asked for in there. All right, so we are back to talking about trees tomorrow. We'll play around with some worksheets. We'll talk about different kinds of traversal, and then we're going to move on to talking about balancing trees. All right, I'll see you then.